Good afternoon, everybody. Please coming back to your seat, and we will start the third session of our course today. Thank you for coming back to this Zoom. Now we will continue our course today with the third session. The third session is Codes over Rings, and it will be delivered by Dr. Intan Muchtadi. The time is yours.
We will start again now with different topic. So I will talk about code over rings. And so this slide I took from the slide from Patrick Solé, his slide presentation for conference non-commutative ring in June 2009. So let me start with in 1948. Shannon published a mathematical theory of communication dealing with the problem of digital communication in presence of natural noise between a source of message and a receiver. So message M is encoded as a string C in F to N, where N is bigger than K. But then it is sent to a channel where it is corrupted by an error word, where E is a factor in F to N, and then received as Y equals C plus E, but then it decoded as M hat. And so the difference between cryptography and coding theory, in cryptography we try to hide the message in a secure channel, but in coding we send the message, but then when we receive it, maybe there contains some errors, and we try to detect and correct that errors. And the code is the set of all code words generated by all possible messages. The integer n is called the length of the code, and the ratio k over n is its transmission rate. And he proved that as long as the transmission rate k over n is less than the capacity of the channel, so then given epsilon, there are long codes, means with n large, such that the probability that m not equal to m hat is smaller than epsilon. But the proof is probabilistic and non-constructive, and the aim of algebraic coding theory is to construct effectively good codes by assuming some algebraic structure on the code. One method is replace the element of a ring, the alphabet, and assume some symmetry, maybe for cyclicity, quasi-cyclicity, then can be represented by an ideal or module structure of the code over some auxiliary ring. So my talk this afternoon will be more technical, more mathematical than my talk this morning. Let us start with linear code over field. So a linear code C of length n over a finite field Fq is an Fq vector space of Fqn. The dimension is usually denoted by k. Its dimension as Fq vector space. And we denote by bracket nkq the parameter of a code. So the code is specified by a basis of the space, a metric G of size k with n with rows these vectors is called a generator matrix. So C will be, the code C will be U times G, where U is vector in FQK. And we have another matrix we call parity check matrix, H, of a code is an n minus k by n matrix, such that C is the null space of H. In other words, C is all vectors x in Fqn where H times x transpose equals 0. And the row span of H will be also a code of dimension n minus k and denoted by C_perp, and we call it the dual code. And for example, if Q equal 2, and if G is a row matrix contains only ones, so if we have the field is F2, and then we have, let's say, a matrix G like this. So it is clear that we will have an N1 code, because then the dimension of the code is 1. It is a low-rate code that can transmit 1 bit of information, can correct n over 2 errors by majority voting. I will explain that later. And we can define the Hamming weight of element x in Fqn as the number of entries where x is not 0. And the Hamming distance between two vectors is defined as the WH of x minus y. And this distance satisfies the triangle inequality that the d of xy is smaller or equal than d of xz plus d of zy. And we can also define the sphere of radius r about x is the set of all y where the distance, it should be xy. The distance from x to y is smaller or equal r. So this x should be y. One of them, I mean. And the minimum distance of a code C is the minimum distance between two factors in C which is not equal. And we call the error correcting capacity T of C is the minimum distance of C minus 1 over 2 and then take the floor. And By the triangle inequality, we can show that the sphere of radius t about code words are pairwise disjoint. So therefore, all received words corrupted by less than t, less or equal t errors are at distance at most one code word. And this minimal distance of a code we usually denote by d, and then the parameter become nkd over q. So the problem in coding theory is if BQ and D denote the largest size of NKD key code, then given N and D, we would like to have this size as large as possible to send as many messages as possible. But we also want, if given N and K, we want D also to be as large as possible to correct as many errors. So there is so-called fundamental problem of coding theory, finding the good trade-off between these two conflicting requirements. And the repetition and parity check codes are two optimal codes at each end of this spectrum. So the BQ of N2 is N-1, quite big, and BQ of NN is Q. And we have this interesting code, so-called cyclic codes. I don't know how, okay. Equal 7 and Q equal 2. And then we make these equivalent classes of from the permutation, say x to 2x, because now Q is 2. So for 0, you multiply by 2, keep 0. But for 1, start with 1, multiply by 2, become 2. 2 multiply, become 4. And then 4 multiply by 2, become 8. And 8 modulo 7, back to 1. And for the third class, 3 multiplied by 2, we get 6. And 6 multiplied by 2, we get 12. And 12 modulo 7 is 5. Okay, you get what I mean? And then from these three classes, we get these three factors. X plus 1 corresponds where the I is 0. So when the I is 0, we get x plus alpha power 0 become x plus 1. And when alpha power 1, then alpha power 2, alpha power 4, and then we multiply all of them, we get this x cubed plus x plus 1. And the last factor is x cubed plus x squared plus 1. And another interesting code is called the self-dual codes. And start with the dual code with respect to standard Euclidean product. We define the C-perp as all the factor where x dot y equals 0. And a code is called self-dual if it's equal to its dual. Okay, let me start with code over rings. Now A is a commutative ring with identity 1. I should say finite commutative ring. And instead of subspace, now we're working with submodule. A linear code C of length n is an A submodule of A power n. It means that for all x and y in C, x plus y is in C, And for alpha in A, alpha X also in C. Then we have also the standard shift operator, and for that one we can get the cyclic code. But then if you shift more, you get the T power L, say, and it means you shift more and more again. Like for cyclic, you just shift AN minus 1 to the front, and then if you want the T square, means you get AN minus 2 in the front, and so on. And we call that code, if the TLC is still in C, we call it as quasi-cyclic of index L, or L quasi-cyclic. And N over L is called the co-index. And we can also have a one-to-one correspondence with polynomial. If M is a positive integer, and then we define this polynomial A with variable y modulo ym minus 1. And say we have a quasi-cyclic code over A of length Lm and index L, and we write it like this, C00 until C0 L minus 1, and then C10 until C1 L minus 1, and so on. And by defining the A power Lm to RL, so you have that from C00 to Cm minus 1 L minus 1 is in ALM. You send it to R power L, C0 until CL minus 1 with variable y, where for each C0 until CL minus 1 is a polynomial in y, and denote by phi of C, image of C under phi. And we get a one-to-one correspond between quasi-cyclic codes of over A of index L and length Lm, and linear codes over R of length L. I should remind you again what is R. R is this polynomial ring. Oh, sorry. How to do this? And for the skew cyclic code,